Data Analysis Part 4. Designing experiments to be as informative as possible and to avoid ludicrous hazards which can cause you to make mistakes when you apply data analysis, if you apply it to data that hasn't been collected and described in a suitable way. Hazards such as Simpson's paradox. Hello everyone, welcome to Part 4 of the MPhil ACE data analysis series. So far in the course, we have said what is data analysis? Well, it's the course to do with how we're learning from data, and I have said that we're going to concentrate on how we learn from data, and in a Bayesian sense, so that we're going to be looking at ultimately methods to get good answers by saying what we know after we have some data to analyze is what we knew before, plus what the new data told us. I've given some example questions for this in the first lecture, and in part 2 and 3 we looked at methods for describing data. So descriptive statistics, principles of good data displays, and some of the hazards of overinterpretation. In this part, I want to look at Simpson's paradox, probably the most important hazard which can happen, or a mistake that you can make when analysing data, and we'll look at how to avoid that. Before I do that, I normally cover in this lecture course some non-essential content, and a thing which I find, well, it would be useful to cover this at the start of the data analysis course rather than put it in at the end when I discover there's spare time because I haven't filled it out. So, here is some non-essential but I think quite useful material on types of knowledge which you might encounter in science or when interpreting data which you read in literature or the news. In this course, we're interested in how we can learn from data. Before we deal with that in more depth, it's useful to ask, what is it possible to learn about a particular subject? And there's a useful quote from Aristotle. You should always look up Aristotle on any subject. He said, the mark of an educated mind is to look for a degree of certainty in one's conclusions commensurate with the subject matter. And this is a useful quote to bear in mind, to remember, because depending on what topic we're trying to look at using methods of data analysis, we can have different levels of certainty are possible about the conclusions. I'm going to talk in this section for 5 minutes or so about the difference between rational mathematical knowledge, where we can expect to have absolute certainty, and empirical knowledge, or knowledge of the real world, where we can at best have probable certainty. And I'll talk also about some different types of knowledge, including constructive knowledge, where the methods of ordinary data analysis on their own aren't going to be exactly everything you need, and you might need a different topic, which will be game theory. Okay, so let's just look at these categories so that when you come across some subject, you know whether pure statistics and that sort of scientific data analysis will be suitable. I mean, it will be for lots of topics you'll find in science and engineering, but let's be aware of which things we can apply them to. So we'll start off by talking about rational knowledge, which I will also call in this section mathematical knowledge. Well, philosophically, rational knowledge includes statements like all red boxes are red. This is a statement where we can be absolutely certain that the conclusion is true, and we can be certain that it's true because this can be completely studied using logic, or we could also say using mathematics. In particular, the type of question we're looking at in this rational knowledge is we're starting with some sort of thought, and we have the thought about what a red box is, and this contains enough information for us to be absolutely certain that yes, it is red. Let's look at a more practical example of mathematical knowledge. If Euclid's axioms are true, then Pythagoras' theorem is also true. Again, this is a kind of mathematical knowledge. It's actually from Euclid's Elements of Geometry, so it's actually it's an example from the book which is in many ways defining for what mathematics is. But again, the point is, we start off with the source of our information that we're studying, its thought, or we have in mind the principles of Euclid's axioms, which includes some rules about how we can take definitions and we can work out theorems, we can work out which theorems are true. And if we start and we say, well, we're in some system where Euclid's axioms are true, in that case we can be certain completely, we have deductive certainty that Pythagoras' theorem does apply. This is great, but you see the limitation of rational knowledge is that or mathematical knowledge, is that it's always relational. It's always starting with, if some principles are true, then some other things are definitely also true. Or we need to have some axioms to start with. The limitation of this is that we can't be certain which of these axioms apply in the real world. For that, we need some additional knowledge. So let's just finalize the thought on this. So I can tell you, but not from mathematical knowledge, that if I'm drawing some lines with a straight edge and a compass on a sheet of paper on a flat desk, then yes, Euclid's axioms do apply, and then Pythagoras' theorem is true. But if you were trying to do the same sort of construction on a curved surface, then Euclid's axioms would not be true. But the question about whether they are true or not, the starting points, whether they are true in the real world, that's not a question for mathematics itself. That's a question for empirical knowledge. So empirical knowledge, this is information you get from, or knowledge you get from observation or experience. And this kind of knowledge does have the useful ability that we can learn things about the real world. I can say, for example, my dog is black, and I can be completely certain about that because it's a single case. I'm obtaining for you knowledge from this photograph of my dog and me about some physical property of the world. The problem with empirical knowledge is that unlike mathematical knowledge, where I know in every case where Euclid's axioms are true, Pythagoras' theorem does apply, empirical knowledge doesn't generalize so well. So, for example, if I try another piece of empirical knowledge, I could try and say something general. I could try and say, all ravens are black. But this would be a claim that goes beyond one or two ravens that I can observe, and it actually goes to all ravens. I've got a photograph up here just to prove it's actually false. It's a statement that lots of people would confidently make, and they'd say, well, yeah, ravens, they're these black things. Well, occasionally, it's not just in fantasy television. Occasionally, you can get ones that are missing enough genes that they're actually these white ravens. And somebody who confidently told you, based on physical experience of lots and lots of black ravens, that all ravens are black, they would have been doing not deductive reasoning where they could be completely certain about the conclusion. They would have been doing inductive reasoning where they could, at best, they could find it highly probable that the conclusion is true. In fact, so and I have a more extreme version of empirical knowledge. I could tell you all lumps of coal, or all lumps of anthracite coal, are black. This would be another general piece of empirical knowledge, but in this case, I would be even more confident about it than most people would be about saying all ravens are black, because not only would I have lots of examples of lumps of coal from which I could make conclusions about the future, I could say more. I could say, well, I actually have knowledge of this big subject called chemistry. And from physical chemistry, physical chemistry is a subject where we've taken, or other people have taken, an awful lot of experience, and we've worked out these rules. And based on these rules, we can say that something which does have the the physical structure of anthracite coal, we'd predict it to be black, because we predict that it absorbs all kinds of visible light. So that's another kind of induction, but still, whereas I could look at one thing like my dog and say that my dog is black, or one lump of coal and say that's black with complete certainty. I could say that from experience. Even in the case of inductive reasoning, where I've looked at lots of things in the physical world and I've said I've learned these rules of chemistry, applying those to things I've not yet seen, that is still at best gives me highly probable knowledge about the truth. Now, in science and engineering, most of the questions which we answer using data analysis are to do with empirical knowledge. We typically have a data set with some records that we've observed something, and we can either do descriptive statistics, in which case we're just we can have absolute certainty to state something about the data we have observed. So in the bottom right photograph, how many black ravens are there? 3, absolute certainty. Or we want to do inferential statistics, and we want to draw conclusions beyond the data set that we've got. In other words, given the bottom right photograph with 3 black ravens and 2 white ravens, what percentage of a set of future ravens might be black? That's something where we don't have absolute certainty. We can at best have probable knowledge about the conclusion. Hopefully you agree with me so far that most of the tasks you get given in science and engineering do involve processing empirical data. If you agree with that, then you might say that, sure, we're mainly worrying about the difficulty, this probabilistic aspect, which comes with taking empirical data and making predictions about the future. But although that seems like the hard part of what we're doing, it's worth bearing in mind that the process we're doing in science, processing data, involves 2 kinds of knowledge. There's obtaining the data, which is observation or empiricism, and there's processing it mathematically, which involves rational or mathematical knowledge. So this, the fact that, although the hard part of what we're doing looks like it comes from empirical knowledge, actually this fact that we're always in science dealing with obtaining data and working with it mathematically is what Immanuel Kant refers to when he describes this important quote about understanding, or about what we can learn scientifically. He has this famous quote: "Thoughts without content are empty, intuitions without concepts are blind." In this Immanuel Kant quote, thoughts without content would correspond to a mathematical method, but you don't have any data to apply it on, and you don't have any data to know whether the rules of the method apply in the real world. The second part, intuitions without concepts are blind, would be to say you've got some data, but no idea how to process it mathematically. So Immanuel Kant says that only through their unison of mathematical methods and obtaining data can knowledge arise, or we could say there can scientific knowledge arise, where we can say something useful in general about the world. Now, you are not obliged to agree with this, but I find it helpful to bear in mind most problems I have to look at in science do involve a mathematical part and a real-world data observation part, and it's by putting them together and applying them to observations of the physical, objective world that we can do useful science. And now I've emphasized there that we are typically interested in doing data analysis of physical, objective properties of the real world. The reason I highlight this is because there's a fourth type of knowledge which you increasingly need to worry about finding in literature, and certainly in news reports, because it doesn't have quite the same nice properties as observing whether lumps of coal are black, or observing other purely physical properties. So the next kind of knowledge you should be aware of that it exists can be called constructive knowledge. So constructive knowledge doesn't come from measurement of the physical world. It comes from the consensus of decision makers, or you might say decision-making agents, or you could say economic agents, or you could say people with free will. So let me give you an example of constructive knowledge. It's the statement, we should all drive on the left-hand side of the road, brackets, in the UK. Now, this statement is true, and it's true purely in virtue of the fact that it's what the vast majority of people in the UK agree with. So anyone who is in the minority and disagrees with the statement, we should drive on the left in the UK, they will have a lot of trouble because they will have a very high chance of being in a serious collision. Whereas the people who agree with the majority that they should drive on the left, they have a very low probability of being in a serious collision. And just by virtue of being in the majority, they're correct about that is what they should do. What you can't do with this type of constructive knowledge is apply it to make predictions as if it was some sort of physical truth. So making observations of this, which side of the road is it safer to drive on in the UK, you couldn't go and apply that as if it's a universal constant and make predictions about France, because you'd get into a horrible mess. Now, the subject for mathematically studying constructive knowledge is actually game theory, and there's a whole business of describing interactive decision-making problems and assigning payoff matrices in terms of the decisions made by each economic agent, or you could say player in a game. And there's a whole business of which decisions are best, and dominant strategies, Nash equilibria, all sorts of jargon terms which we don't need to worry about. What we do need to worry about, or know anyway, for the purpose of this course, is that when you're dealing with interpreting data which comes from the decisions made by people, that is a subject which needs fundamentally more mathematical methods and more consideration than just applying orthodox statistics or the kinds of things that we're looking at in this course. In this course, we're looking at methods really for interpreting scientific data or engineering data, making comments about physical products, not making predictions about the behavior of people, which is really for economics and not for a scientific data analysis course. Still, I do think constructive knowledge is such an interesting, different topic, different type of knowledge from mathematical or empirical knowledge, that it's worth having a few more examples. The whole of spelling or language is constructive knowledge. So, for example, the fact that we should spell the colour green in English, Green, and not Grene, is purely is constructive. As long as we all agree on a particular spelling for that and for other words, we get when we say this is how we should spell this word, we get the large benefit of being able to communicate with each other efficiently. If we can't agree on how to spell things, then we have a complete mess. You can probably argue that a good deal of conclusions in economic theory are constructive, or they come about purely from the consensus of people involved. You can argue that why money has value is simply because people agree that it does. But again, this is a discussion for economics, or maybe for Austrian school economics, not for scientific data analysis. But constructive knowledge, just be aware, don't directly apply the same rules intended to look at the effectiveness of drug treatments for a disease to the decisions made by people. Okay, there's a fifth kind of knowledge which I want to briefly mention, revealed knowledge. Revealed knowledge is self-evident. So why is this? How is this different from, say, mathematical knowledge that comes from principles or empirical things that you observe? Well, certain systems simply have some knowledge, and they simply have to accept that it's true. I've got a couple of pictures to illustrate this. Well, the one on the left is obviously St. Paul on the road to Damascus, where, previously not being a very good man, he is struck by a revelation of the way that he should live and what he should believe. And once he's been struck with the revealed knowledge, well, you can essentially treat this as foundational for him. From then on, this knowledge is true simply by virtue of the fact that he knows it. It's been revealed to him. It's not questionable. It's what he's going to use as the basis for the rest of his reasoning. Why is this potentially something you need to worry about in science? Well, I've put a picture on the right-hand side, which you should recognise as HAL, or is it HAL 2000? Can't remember. From a Space Odyssey. HAL is a computer who has problems because he's struggling under some unquestionable rules which he's been given to work with. The laws of robotics, and because HAL is he's been programmed with these knowledge with the laws of robotics, he has no choice but to treat them as true. This leads him to make some extremely troublesome decisions and act in a very dangerous way in the rest of the story. How is this relevant to science? Well, sometimes you have a computer program or a mathematical method, and this mathematical method makes some assumptions about the nature of the data which it's being given to process. So you will not be able to get conclusions from a particular data analysis method which break the rules which are introduced simply by applying that data analysis method to your problem. Let me give just one example of how applying a mathematical method introduces some assumptions which we then can't get rid of, or we can't get a conclusion that avoids those assumptions. If in industrial statistics we apply a t-test to see if there's a difference in the value of a measurement between one set of measurements and a second set in a different situation, if we apply a t-test, we've introduced an assumption that the difference in the mean values comes from a physical process which gives you a Gaussian distributed difference. If the physical process that gives you those measured values doesn't have that property, then the mathematical method we've applied assumes it does, and there's no way we can remove from our conclusion the influence of that assumption, and it might give us a wrong answer about whether the difference between the two situations is significant or not significant. So be aware that sometimes the choice of what mathematical method to apply to a particular data set can effectively add information that wasn't previously there, and possibly affecting our conclusions. One of the advantages of Bayesian data analysis, which we will be concentrating on in this course, is that although we do make assumptions, it's going to be called prior knowledge. When we make assumptions using Bayesian data analysis, we are forced to write them down so that we know what assumptions we're making. This gives us a good way of then presenting our conclusions, where we've clearly written down both our assumptions as well as the data set we've applied it to. And in this way we get conclusions which are as transparent and accurate as possible. Right, so that is the end of my commenting about types of knowledge and what it's possible to learn in particular problems, and the warning that we're especially interested in data analysis for physical science type problems. Now, within physical science, we're now interested in design of experiments. How do we collect data so that it's as useful as possible? There are, in fact, two especially bad phenomena which, if you don't plan to avoid them or to study if they've come up, then they can lead you badly astray. These bad phenomena are Simpson's paradox, which we'll look at now, and regression to the mean, which we'll look at after we've talked more about probability. let's start out with Simpson's paradox, an example of what it is, and how we plan to avoid it affecting our experimental conclusions. So, the story is this. Imagine that you go to your local doctor, your general practitioner or GP, and you persuade the doctor somehow to hand over all of his patients' files, and you for the good of science, and you rummage through the files for your general amusement. And one of the things you observe is that, this is quite an interesting conclusion. You think you discover that 30% of the patients who have recently been treated with medication for gout have symptoms of gout, such as poor blood circulation in the feet, whereas only 2% of other patients have these symptoms. And you think to yourself, does this mean that the medication for treating gout is actually causing gout? No. Or in other words, do you believe the theologian Martin Luther, who said that medicine makes men sick? Is that the conclusion you draw from this data? Well, if you have a good faith in modern medicine, you say, of course not, because the medication for treating gout was only given to the people who were suffering from significant symptoms of gout. And therefore, of course, they, even after they've been treated, they're still a little bit less well than the other patients. That's because, in terms of gout symptoms, that's because they were much sicker before they were given the medication. But of course, the medication helps. That's what you would probably conclude, as long as you had a good faith in modern medicine. Of course, if you got the same numbers, except for a different apparent possible cause in the doctor's notes, if you saw that 30% of the patients he described as heavy port drinkers had symptoms of gout, and only 2% of the patients who were not heavy port drinkers had symptoms of gout, well, then you might reach a quite reasonable conclusion that maybe drinking masses of port isn't the best thing. But this is a problem, because apparently the same data, in order to work out what's going on, apparently we're having to put in a lot of our own information, and that's not really the best way that we should be doing dispassionate scientific data analysis. So, what on earth do we do? How do we avoid Simpson's paradox? Well, we think about it when we try and do design of experiments. And the answer which we're going to get to is you need to invent some sort of system like a randomized controlled trial. This will hopefully allow you to distinguish correct conclusions. Before we get to that, though, let's look at start of Chapter 3, Design of Experiments. I couldn't help but start this section in the notes with a quote from Ernest Rutherford, the legendary Cambridge professor, or the Cavendish professor of physics. Rutherford said, quite unhelpfully for the purpose of my giving this course, you might think, he said, if your experiment needs statistics, you should have done a better experiment. Alas. Sometimes you have an experimental result which is so striking that you can't possibly have any ambiguity about what caused it. Rutherford was, of course, praising his own famous backscattering experiment, in which the direct backscattering of alpha particles from gold foil disproved a particular older theory of atomic structure, and pretty much made it necessary for the structure of the atom, the model to be updated to the nuclear model of the atom. In general, however, we do need statistics, and let's look at another case. In order for me to tease out more details of Simpson's paradox, let's look at a case of Simpson's paradox happening with numerical data. So, section 3.1, Simpson's paradox and the difficulty caused by confounding variables. So, More precisely speaking, Simpson's paradox describes a trend which appears when two or more sets of data are considered together, which is different from the trend in each set of data on their own. And it occurs because a sometimes unexpected confounding variable is different between the data sets. So we have this example here of some numerical data which features Simpson's paradox. We have here a plot, and on the x-axis of this plot we have number of hours spent revising for a test. On the y-axis we have the score out of 10 received in the test. And you have here two different coloured sets of data. The blue blobs correspond to art students, who spend between 1 and 4 hours preparing for the test, and they get between 6 and 10 marks for the test, increasing with the number of hours they spent preparing. And you've got in red dots the engineering students. They spend between 8 and 11 hours preparing for the test, and they receive between 1 and 4 out of 10, increasing with the number of hours they spent preparing for the test. If you have the students separately, you can easily see the trend that's going on here. You can see that more hours spent preparing for a test gets you a better mark, as you would hope to see, and you can also see that you get students taking art score fundamentally higher marks than students taking engineering. Even though your arts students all spend less than half the effort on their work than the laziest engineer, nonetheless, they get higher marks just because art is a fundamentally easy subject. Now, because you have between these two types of students two kinds of things are varying, both the number of hours they're spending in preparation for the test, but also the subject they're doing, if you forget one of those differences, say the subject that they're doing, and you just fit the dashed best fit line to the data of hours spent revising versus test score, you get this decreasing line. This apparently gives you the conclusion that increasing amounts of revision is associated with lower marks. Now, the key to understanding what's going on here is that this is correct, but only part of the conclusion, because you've lost some information about a confounding variable. Of course, the full conclusion would be the result would go up within the same subject, but the dashed line, which predicts a correlation of lower test marks for more hours work, it is partly correct, simply because if I point across the building and tell you that a particular student has done a large amount of revision, that increases the confidence in your mind that I'm pointing at an engineering student who, because they're doing a hard subject with challenging tests, is actually likely to get a lower mark than some student that I pointed at said they did very little work, and you say, oh, they're going to be a generously marked art student. So that's the key to understanding Simpson's paradox, is that you, when you forget a confounding variable, like what subject is being done in addition to the number of hours spent revising, you get a correct conclusion, but it's only part of the conclusion. The key to avoiding Simpson's paradox affecting your data is to use randomization where possible, so that you design an experiment whereby you expect any variables other than the one that you're, say, controlling. For example, you might be telling students how long to spend revising. You want other variables which might affect the result to average out to be the same in both of your groups. Right, further along in section 3.1 we have the most numerical example for Simpson's paradox in this chapter. So this is a example from the literature, a true study on the success of different surgical methods for treating kidney stones. So we have some data which is in one case aggregated and another case not aggregated, and we believe, I believe it shows Simpson's paradox with quite serious implications for making providing good advice about medical treatment. So the data is this: patients with kidney stones selected either treatment A or treatment B, based on their doctor's advice. I believe treatment A was open surgery and treatment B was keyhole surgery. But anyway, treatment A and treatment B. Treatment B, if you look at, there were 350 patients chose each type of surgery, and apparently a higher percentage of the patients were treated successfully, for some definition, some medically suitable definition of success, with treatment B. So apparently treatment B works better. However, there was a confounding variable affecting these results, because these results were from an observational study. The results were obtained after the doctor and the patient had decided on a treatment which depended on the size or severity of the kidney stones. And it happened that they tended to prefer treatment A, open surgery, for big kidney stones. Big kidney stones, I believe, means bigger than 2 centimeters in diameter, so very serious ones. Now, the disaggregated data in the second table shows you the effect of treatment A and treatment B on small and large kidney stones separately. And here you see treatment A actually works better for both small and large kidney stones. The apparently worse performance of treatment A in the aggregated data, because it was given to a bigger number of patients who had large kidney stones, which were harder to treat and less successful for both methods. In fact, the treatment A gives a better outcome for patients who have pre-existing both a small kidney stone or a large kidney stone, and this is what the authors of the study who observed this Simpson's paradox in the aggregated data, this is what they realized. Great. A couple more remarks on this subject. Well, first of all, I'm assuming that this success statement is a perfect description of what makes the treatment better. In fact, it's also possible that maybe the treatment B, a keyhole surgery, had a faster recovery time, in which case maybe that's advantageous even if it has a lower overall success rate for both a small kidney stone or a large kidney stone, maybe because it's better tolerated. So we're ignoring that complexity. We're just assuming that success is the thing which describes the treatment being better. The other thing I'm assuming, and this is the case, I believe, in this study, is that the small or large size of the kidney stone was pre-existing prior to the choice of surgery. And then the treatment A, once you knew whether it was a small kidney stone or a big kidney stone, in each case treatment A was better, so that's the one that should be recommended. However, just to show you a different way this data might have happened, if treatment A happened to be a kind of surgery with a long waiting list, and it actually and all the patients came in with the same size kidney stones, but more of the treatment A group, their kidney stones got bigger while they were waiting. In that case, the aggregated data would be the correct one to use to observe that treatment A was actually the cause of a lower success rate. Now, that's not what happened in this particular study, but I'm indicating that it's difficult, taking observational data, to know whether this confounding variable exists or not. In this medical case, in this case of kidney stones, the people who did the analysis knew that small or large kidney stones was an important factor, and they specifically disaggregated their data to look for to ensure that it didn't influence the conclusion wrongly. So, what are we to do if we don't have that kind of medical insight about which factors are important? Well, the answer is that what you'd like to be doing is getting the results from a randomized controlled study. You can read about those in section 3.2 of the notes, but when I say randomized controlled study, this is a kind of, and this is only sometimes possible when both treatments are equally ethical to give. In other words, we're not thinking that one of these surgeries is bad. If they both are pretty decent, we might be able to do an experiment where we do the following kind of trial. So 3.2b, which is what I will call a randomized controlled study, is a study in which the investigator exercises control in the sense of having a control group as well as an experimental group which differs in just one way, and the investigator assigns experimental units, that means people in the patients in this case, to each group in some randomized way, for example by flipping a coin or alternating between them. Now, in the case of the kidney stones data, that would eliminate the problem of patients with their doctors choosing with a bias so that the more seriously ill patients chose a particular treatment. In a randomized controlled study, pre-existing differences between the experimental groups will tend to average out to zero. And so the only, once you have a large enough sample of patients in each group, so the only differences in the outcomes will be the ones caused by the choice of which treatments to give. This business then of doing a randomized controlled trial prevents the results from being biased by confounding variables such as the variation of pre-existing kidney stone size, which affected the results in example 3.1a. So, by comparison, what we often have to work with are observational studies. We often get data from this. These do not randomly assign, or did not randomly assign individuals to experimental groups. Observational studies can be valuable because often randomized controlled studies do not exist, or they contain few results, or they're impossible to carry out because of cost, or time, or ethical considerations. It's not possible to do a randomized controlled trial when you believe one of the treatments is not as good as the standard of care, for example. But be aware that an awful lot of data that you do encounter, especially in news, but also in literature, these are observational studies, and they very often contain variations between groups, which lead to a bias in the average result observed for each group. In general, it is impossible to attribute cause from an observational study because a correlation does not indicate causation necessarily. There are some other causes of correlation apart from Simpson's paradox. Other causes such as selection bias, which we'll come on to look at before we get further into this course. We'll come on and look at that in the next lecture. Right, so we will in the next video look at sample bias and finish off the basic problems which we can try to avoid through proper design of experiment. Before we do that, let's just finish off a couple of important terms for things which can badly affect your experiments related to these sorts of kidney stones or Simpson's paradox example. Types of unhelpful variables. I've used the term confounding variable. That is a technical term. A confounding variable is something which varies between your treatment group and your control group, which you didn't control for, and which introduces an actual physical extra effect which throws off your conclusion as to how good the treatment is. Right, and other terms, 3.2.2, methods of randomization. So, assuming we have got an experiment where it's possible to assign patients to one treatment group or the other, or an industrial equivalent to use one particular processing technique on a component or another, we need a method of randomization. A few commonly used, very easy to understand, a coin flip. Each experimental unit is assigned to one group or the other by a coin flip. This provides randomization, but obviously not necessarily equal group sizes, and it's not particularly well planned because of that. Much better method, 3.2.2c, sorted random numbers. So for each experimental unit, get the computer to draw a random number and assign the top 50% of the values to one group and the other 50% of values to the other group. This guarantees equal group sizes, and also, unlike some of the other methods like assigning by pairs, sorted random numbers conceals from the investigators which group the second, third, or fourth, etc. Unit is being assigned to. Anyway, lots of methods for randomly assigning your experimental units to a control group or a treatment group. The point is, with randomization, the effect of all extraneous variables, for example, pre-existing levels of health, or in an industrial case, the quality of a component. Extraneous variables should average out to 0, or the effect should average out to 0. The extraneous variables should average out to be the same in your control group and your treatment group. If you have observational studies that are not randomized, it's very likely a confounding variable exists that causes an effect that doesn't average out to be the same in your control group and your treatment group. What else? Oh, it's useful measuring, discussing the terms prospective and retrospective. So a prospective study is one which is planned in advance. So in the case of the medical trial of treatment A or treatment B, the treatments are assigned in advance and then the subjects are followed. Prospective studies are important because they can be done as a controlled experiment, hopefully as a randomized controlled experiment. A retrospective study is an examination of existing data, or it's called an observational study. It doesn't come with the ability to randomly allocate experimental units to one treatment group or the other. Therefore, they're quite likely to contain confounding variables. They can also contain selection bias, but we'll briefly do that when we recap this design of experiments to avoid some problems at the start of the next video before we move on to probability.